Inner product spaces. Let us just review some calculus contents that you learned before. Definition of norm or length of a vector in the n space. The length or norm of a vector like v with components v1, v2, v3, vn in n space is defined as, so remember that in calculus, you use just one line on the left, one line on the right. But officially, when we are introducing norm, we use double lines on the left, double lines on the right. Is equal to the square root of v1 to the second plus v2 to the second plus vn to the second. So you're basically taking all of these components and raise them to the second power. The length of a vector is also called the magnitude. Recall that if the length of the vector is equal to 1, then you call it a unit vector. If you have a vector that has no magnitude equal to 1, still we can make it into a unit vector. No one's stopping us. Take a look at 5 space, r to the 5th, the Cartesian product with r with itself 5 times. The length of this vector is not 1, everybody. You can easily calculate the length of this vector. It is equal to square root of 0 squared plus negative 2 to the second plus 1 to the second plus 4 to the second plus negative 2 to the second, which is square root of 25, which is 5. But I can make this into a unit vector by dividing the component of this vector by its magnitude. So take the magnitude of the vector and divide every component by that magnitude. It becomes a unit vector. Why we are interested in doing that? Because it helps us to scale a matrix. Especially in machine learning, deep learning, we prefer to scale vectors. The property of the length. If I ask you to find the length of a vector which is multiplied by a scalar like c, you can say that, hey, I just find the length of that vector and then multiply it by absolute value of c. Absolute value of this number. So if this number is negative, it becomes absolute value of negative, which becomes positive. What is the proof? Well, if I have a vector like v with v1, v2, v3, vn, the scalar multiplication says, hey, I'm going to multiply every single component by c. That's how you end up with c v1, c v2, and c vn. So if I take the magnitude or norm or length of this vector, it's equal to square root of cv1 to the second plus cv2 to the second plus dot 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 plus cvn to the second. But this can be written as absolute value of c. Why is that? Because I can factor out c squared. But remember that the square root of c squared is not necessarily equal to c. If the domain is not positive, then you have to put absolute value sign. So square root of c squared is equal to absolute value of c. That's how we end up with absolute value of c times square root of v1 squared plus v2 squared plus dot 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 vn squared, which is nothing but, by definition, the magnitude or norm of v. So you have absolute value of c times the magnitude of v. So as I mentioned before, if you have a vector which is not a unit vector and it is non-zero, you can definitely make it into a unit vector. You can scale it all the time. U can be written as v divided by the magnitude of v. This vector u is the unit vector in the direction of vector v. For example, you have vector v, 3, -1, and 2. Verify that this vector has length 1 if you write it as the unit vector. So v divided by the magnitude of v is equal to, here you have 3, -1, and 2, which is your vector, divided by square root of 3 squared. You take the very first component, raise it to the second power. You take the second component, raise it to the second power, and you take the last component, raise it to the second power, add them all together. It becomes 1 over square root of 14, which is a scalar. Guys, this is your c. c times v, 3, -1, and 2. This is 3 divided by square root of 14. You just distribute into each component. -1 over square root of 14 and 2 divided by square root of 14. Indeed, this is a unit vector. Why? Because if I take the square root of 3 divided by square root of 14 to the second plus -1 over square root of 14 to the second plus 2 over square root of 14 to the second, it becomes 9 plus 1 plus 4, which is 14. So you have square root of 14 divided by 14, which is square root of 1. And as you know, square root of 1 is equal to 1. So this guy indeed is a unit vector. Very good. So what is the definition of distance between two vectors? The distance between two vectors u and v in n space is defined as d, which represents the distance, u and v, which is equal to magnitude or norm of their difference. So if I ask you to find the distance between two vectors, you're going to subtract their corresponding components and then find the norm. This guy has important properties. First of all, the distance between two vectors cannot be negative. It at least is 0 or a positive number. The distance between two vectors is 0 if and only if those two vectors are the same thing. And finally, the distance from the very first vector to the second vector is the same as the distance from the second vector to the first vector. So if you have two vectors, it doesn't matter if you find the difference between u and v or v and u, the distance is going to be the same. Suppose I ask you to find the distance between these two vectors. The distance between u and v is equal to the magnitude of u minus v. Perfect. So we can do the subtraction. Again, the order is not important at all. -1 minus 2, comma, -4 minus 3. You get -3 and -7. Then you find the magnitude. Get square root of -3 to the second plus -7 to the second, which is square root of 58. So this is the distance between these two vectors. Remember that in one-dimensional world, like when you have a real line, you can find the distance between two numbers, like the distance between 1 and the distance between 1 and 7, these two numbers. The distance is the absolute value, the difference between 1 and 7, which is 6 units. So then we generalize the idea to the two-dimensional world, three-dimensional space, four-dimensional space, and we need to have a better definition. So it's exactly coming from one-dimensional world to two-dimensional world to three-dimensional world and so on. The concept is the same. What was the definition of dot product in n space? Suppose you have two vectors, u and v. U dot v the dot product or inner product between u and v, you're going to just take the corresponding components, multiply them together, and then add them together. This gives you the dot product between two vectors. Suppose I give you two vectors, u and v. The dot product is 1 times 3 plus 2 times -2 plus 0 times 4 plus -3 times 2, which is -7. The dot product between two vectors. You had some important properties for the dot product, as you remember. It is commutative. The dot product between u and v is the same as the dot product between v and u. You can just verify this. It doesn't matter which one comes first, 3 times 1, -2 times 2, 4 times 0, 2 times -3. It doesn't matter. Order is not important. You can switch these basically. U times v is the same as v times u. You can distribute dot product over summation of two vectors. U dot v plus w is u dot v plus u dot w. If you're finding the scalar multiplication of C and the dot product between two vectors, it's basically grouping CU dot product V or grouping CV dot product U. So you can basically move this C inside and group it with the first vector or the second vector, not both of them, everybody. You cannot distribute this over dot product. It is not CU dot CV. That is wrong. Just one of them. And finally, one important property that we learned in calculus, the dot product between V and V is equal to the magnitude of V to the second power. How do we see this? This should be very easy for you. So if you have vector V, like V1, V2, V3, Vn, V dot V is equal to V1 squared plus V2 squared plus V3 squared plus the rest of the components raised to the second power. This is very easy for you to see. Vn to the second power. So if I ask you to find the magnitude of V, you're going to say that, hey, I'm just going to take the square root of each one of these components to the second power. So this is V1 to the second, V2 to the second, V3 to the second, plus finally Vn to the second. But what is this guy? Inside the square root, what I have V dot product V. So this is basically the square root of V dot product V. Well, okay. The magnitude of V is equal to square root of V dot product with V. So if I raise these to the second power, I get this guy back. Magnitude of V to the second power is equal to, if you raise this to the second, you get rid of the square root. You get V dot V. And please note that the dot product between V and V is never zero, is never negative. It's either zero or it's positive. It can be zero if and only if V is the zero vector.